This whole assignment is related to the DC electricity, and I have solved the first 24 questions, which I will share with you at the end of the session. And today we'll solve from question 25 and onward. So question 25, an orange shell is made by inserting a magnesium and a copper electrode into an orange. The orange shell acts as a source of EMF electromotive force, which can be used to power a clock. The following measurements were obtained from the circuit. The EMF is there, the potential across the clock, and the current is there. We have to calculate the internal resistance. So that the internal resistance is about 20 kilo ohm. So how we can show this? Like the maximum voltage which the battery cell can provide, that is a EMF. Then there's an internal resistance, that is R, and there's external resistance, which is capital R. And they mentioned the current here in the clock. So your clock is there. This external resistance of clock. So the current in this clock is 4.2 microampere. So this will be 4.2 into 10 to the power minus 6. The EMF is 1.79. The potential across the clock means the output voltage. This voltage is 1.72. So how much voltage is lost here? Like 0.07 is actually lost within the internal resistance. So what is the formula? The total EMF is equals to voltage drop internally, which is I and small r, plus the voltage drop externally, which is V. So EMF is 1.79, that's a maximum voltage. The current in the resistor, or the current in, because the same current will flow through the internal resistance I, that is 4.2 into 10 to the power minus. So we'll write as 4.2 into 10 to the power, because it's microampere. So 4.2 into 10 to the power minus 6 times the internal resistance RV, and plus the external voltage, that is 1.72. So this 1.72, it will move other side. So this will be 1.79 minus 1.72 equals to R, and that because 4.2 exponent minus 6 is multiplied, so other side will be divided. So it will be 4.2 to 10 to the power minus 6. So when we divide, we'll get the internal resistance, which is 16,700 ohm. That's a value for R. So it's about 20 kilo ohm, like closer to 20 kilo ohm. Then calculate the power output when it is used to power the clock. So P power is having different formula. P equals VI, P equals I square R, or P is equals to V square. So here we have voltage and current. So we can use power is equals to the product of voltage and current. The output voltage, the voltage across the clock is 1.72. And the current in the clock is 4.2 into 10 to the power minus 6, as it's a microampere. So we multiply 4.2 exponent minus 6 times 1.72 equals to 7.2 into 10 to the power minus 6, and the unit of the power is watt. So 7.2 exponent minus 6 watts. The next part, the EMF was measured. The EMF measured was obtained by removing a clock and connecting a voltmeter with a resistance of 1.7. This is exponent 1.7 into 10 to the power 7 ohm across the electrode. Discuss the suitability of this method. Whenever we want to measure the voltage, because if we draw a current from the battery, the voltage will drop internally. If we don't draw any voltage from the battery, if we don't draw any current from the battery, then there will be no voltage drop internally. So if we connect a voltmeter in parallel here by removing a clock, and the resistance of a voltmeter is 1 into 10 to the power 7 ohm. So we have to discuss whether this resistance is suitable. So normally what we do, we compare the internal resistance with external resistance. So internal resistance, when we worked out the internal resistance, it was about 16,700 ohm. But external resistance is about 1 exponent 7. So external resistance is very high compared to internal resistance. And the total resistance of a circuit will be high as well, because as our internal and external resistance are always in series with each other. The total or the combined resistance of a circuit will be equal to capital R plus a small r. That will be the combined resistance. So total resistance of a circuit will be sum of internal plus external. This is smaller, but external is very high. If the external is very high, the total resistance of a circuit will be high. When high circuit resistance, then the current in the circuit will be very low. As a result, when the current is low, what will happen? Negligible current is there, or very small current is there. So very small voltage drop internally. If the voltage drop internally is like very small, it means the voltmeter records same value as the EMF of this cell. So the points you will mention, like external resistance or voltmeter resistance is higher than internal, and then the very small current or a negligible current as the total resistance is very high. As a result, there will be very small voltage loss. And when voltage loss is very small, because we have the formula that EMF is equals to IR plus V. If this value is very small, like it is approximately zero, so we can say EMF is equals to V. Means what EMF we have, same voltage the recorded by the component. So in question 26, the photograph shows the decorative lights, and all these lights are connected in parallel. The student is asked to determine whether the light contain a filament bulb or a light emitting diode. She set up the circuit as shown, because if it was having a filament bulb and we sketch a IV graph for this, because for filament bulb, its resistance increases with, if there was a filament lamp or a filament bulb, its resistance increases with temperature. And for IV graph, the slope decreases, because the slope of IV graph is reciprocal of the resistance. So if it was a filament, then what will the shape of the graph? The shape of the graph will be like this. Like initially it is constant, but then the temperature increase, so the resistance increase, so slope will decrease. But if it is a semiconductor diode, the slope also represent the reciprocal of the resistance. But what will the shape of the graph? It won't start at, like at a certain voltage, it start to conduct. Before that, it's not conducting. And then the slope start to increase. As the slope is increasing, it means its resistance is decreasing. This will be the shape of a semiconductor diode. So by plotting a IV graph, student can identify which component is connected. So student is asked to determine whether the light contain a filament bulb or a light emitting diode or LEDs. She set up the circuit to obtain the graph. So the graph appeared to be like this. Which one is connected? Filament bulbs are there, or in these decorative lights, filament bulbs are there or light emitting diode? What is present here? LED or the filament bulb? By looking at this graph, what you can conclude? Is it light emitting diode or a filament bulb? Yes, so that's right. It's LED. Why it's LED? Because the shape of a LED does not conduct until at a certain voltage, and then it start to conduct, and then slope is increasing. So it means resistance decrease. If it was a filament bulb, it will start with the origin, it start to conduct, and then the temperature increase, so resistance increase, so slope start to decrease. If it was a filament. The student conclude that LEDs are there, not a filament bulb. Explain why this conclusion is justified. Like how student can say that there is an LED, light emitting diode, rather than a filament bulb. So first thing, if it was a filament bulb, the graph will start with the origin, and when we increase the voltage, the current will also increase, and the resistance also increase. But because if it's a semiconductor diode, so it does not start with origin. It will start on from x-axis, any value from the x-axis. And initially, in this part, normally as a we are increasing a voltage, diode is not conducting any current. So it means diode is having an infinite resistance, very high resistance. That's why even though we increase the voltage, but the current does not increase. The next part, discuss the distribution of the readings. Here, like we have to just comment on the readings, how the readings are taken. First thing you can see, the spacing is not same. Like some readings are some values are very close, some values are far. So what does it shows? It shows that it is not at a taken, readings are not taken at a regular interval. That is one thing. So when we comment on this, you can see some points are very close to each other. It means reading are taken just one after another for voltage. And some points are far away. So it means there is no regular interval. That is one thing. What else is there? The second thing you can see, more readings are taken near the curve. What is the reason? So that we can easily recognize the trend. So more readings are there near the curve. And how this will be good? We can easily recognize the trend, or we can draw a line of a best fit, or a curve of best fit curve can also be drawn. Determine the resistance of a single LED when the total current for to set is 15 milliampere. So 15 milliampere is there, and 15 milliampere is the total current. But you can see they mention in the beginning these LEDs are all connected in parallel. And how many LEDs are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So these are 12 LEDs are there, and we want the current in each one. We want the resistance of each. So first what we will do, the total current, because the total current will divide between them. So there are 12 LEDs. What total current enter? Like example, 1.5 milliampere was there, 1.5 into 10 to the power minus 3. That will divide between them as they're in parallel. So the 1.5 into 10 to the power minus 3 divided by 12. This will give us the current in each LED. Or if it was 15 milliampere, because the value 15 milliampere. So it will be 15 milliampere divided by 12, not 1.5. So this is 15 into 10 to the power minus 3, and that is divided by 12. So we'll get as 1.25 into 10 to the power minus 3. So we have the current. Now, how to work out what is the voltage if the current is 1.25 exponent minus 3? So you have to use the graph here, like 1.25 milliampere. So 10 boxes equals to 5, so each box is 0.5. So 1.25 So this one is zero point 0.5, then 1, 1.5. So between zero point 0.5 and between point between 1 and 1.5, there will be 1.25. So we draw a line from there. And for this axis, each box is actually representing 0.02. So this will be 70, 1.7. It looks like 1. And this is a this is a graph for the total current. Sorry. So if it's a graph for total current, so I don't have to take individual because student plotted a graph for total current and voltage. So I don't have to draw a line from 1.5. I have to draw a line from 15 because student did not plot the graph as they mentioned. Student plotted a graph between voltage and current, not individual current and voltage. That's why I should not take 1.5. I should take as or 1.25. I should take as 15 because 15 milliampere is a total current. So this will be 1.9. So 1.9. So what actually happened, like these LEDs are there, light emitting diodes. So these all LEDs or light emitting diodes are connected in parallel. I just draw three of them. So student is having a battery and with this battery is having an ammeter and a voltmeter. So the voltage, when the current, the total current is 15 milliampere, the voltage we work out from the graph, the voltage was 1.9. Because they are all in parallel, so each will receive same voltage 1.9 volts. So we have the voltage and how to know the current. The total current will divide between the 12 LEDs, light emitting diodes. So that's why we did 15 divided by or 15 milliampere, which is 15 into 10 power minus 3 divided by 12. So that was 1.25 into 10 power minus 3. That is a current in each and voltage we already know. So we can use the resistance, find the resistance by taking a ratio between voltage and current. So voltage is 1.9 and the current is 1.25 into 10 power minus 3. This will give us the resistance of this LED, which is about 1470 ohm. Is it clear this one? In question 27, which of the following shows a derived unit expressed in terms of SI base unit? So we have to work out which one is a derived and represented in terms of the base unit. So Coulomb is basically ampere is the SI units for length, that is meter, time is second, mass of a substance is kilogram, kg, and electric current is there, that is ampere, absolute temperature, that is in Kelvin. So here these are the base units, meter, second, kilogram, ampere, and other two are there, candela, that is a light intensity and amount of substance mole, but you're not using that. So when we check option A, its Coulomb is ampere into second. So it's right because we have the formula current is charge divided by time. So charge is current multiplied by time, that's it. And current is ampere and time is second. And both ampere and second are the base unit and Coulomb is a derived unit. So the question is which of the following shows a derived unit expressed in terms of base unit? That's A. Why not B? Because even though like resistance is a ratio between voltage and current, voltage is volts, but volts is not the base unit. Volt is a derived unit. Ampere is a base unit, but volts is a derived. That's why it's not volt. And then volt equal joule coulomb. So both are derived. Watt equals joules per second. That's also both are derived. One is base unit, another one is derived joule. Here both are derived. Here both one is derived, one is base. Here both of them are base units. In question 28, the circuit contained resistor R. What is the resistance of R if the potential across it is 2? There are different ways to solve such questions. Like example, what you can do. If you have the voltage here too, how much voltage will be there across the 5 1? If the total EMF of the battery is 12, as they are connected in series the potential difference divide between the component. If one component out of 12 it is having 2, what is the voltage across the other component? So that will be the remaining out of 12, 2 are here, so remaining 10 volts will be here. Now we have the voltage and we have the resistance, so we can find current. So V equals IR. So voltage is 10, current we don't know, and the resistance is 5. So 5 is multiplied, other side divide. So 10 divided by 5, 2 ampere. So there will be 2 ampere here and same 2 ampere here. Because they are in series, so the same current will return back. So we have the voltage, we have the current, both are 2 and 2. So it will be 2 divided by 2, which is equals to 1 amp, 1 ohm, because the resistance. That's why option B will be the right answer. So in series, the current is same, voltage divide, and in parallel, the voltage is same and the current divide between the components. The next is a circuit contain a battery of 4 cells in series, each of EMF 1.5. So there are 4 cells, each is having a voltage of 1. So this will be 1.5, 1.5, 1.5, 1.5. So what is the combined EMF of this combination, this battery? Each is 1.5. So what is the total? Yeah, that's right. That's equal to 6 volts. The total is 6. And 3 coulomb of a charge flow, we need the energy. So we have the formula voltage is equals to work done per unit charge, or energy transfer by 1 coulomb of charge. So voltage into charge will give us the energy transfer or work done. The voltage is how much? That is 6. And the charge is 3. So 6 multiplied by 3, that's equal to 18. And the unit will be joule. So option D will be the right answer for this. In the next question, the thermistor are semiconductors. So for what happened for semiconductor? For semiconductor, as the temperature increases, its resistance start to decrease. That can be used in control circuits. The resistance of thermistor depends on temperature. Sketch on a graph the axis is below to show how the current varies applied potential for a negative temperature coefficient thermistor. What is the meaning of negative temperature coefficient? It means the resistance and the temperature are inversely proportional. So what will happen if you the slope of I and V graph, when current is on y-axis and voltage on x-axis, the slope is reciprocal. So as the temperature increases, its resistance start to decrease. If the resistance decrease, the slope will increase. So if we sketch the possible shape of this graph, and we have to use both axes, the positive and the negative. So initially constant, and then the slope start to increase. Same thing the other way around. So this will be the IV graph for a thermistor. But what if they change, instead of thermistor, they say filament? So what will the graph for the filament? Filament bulb resistance increase, the slope decreases. So that will be the graph for filament. If the same question, they ask for a semiconductor diode. So it won't start, and for a diode only one axis because it allow the current only move in one way. So this will be for diode. And if we have an ideal conductor, means the material which resistance does not change, so it will be a straight line. So these are the four graphs you should know. Then explain why the resistance of a negative temperature coefficient thermistor changes as the potential increases. So when we are increasing a voltage, why the resistance is changing or resistance is decreasing? So whenever we increase the temperature, whenever we increase the voltage, not temperature, explain why the resistance of a negative temperature coefficient thermistor changes as the potential increase. So as we increase the voltage, why its resistance is decreasing? So what actually happens when we increase, like say this is a thermistor and we connect with a supply, a variable voltage supply we connect. When we increase the voltage means we are providing more energy to the charge. When this charge is moving and actually the electrons are there, conventional current is from positive to negative, but in practical the electrons are there. So when these charges are moving, like these electrons are moving, and inside there are particles, atoms are there, structure is there. So as a result, what will happen? This electron or the particle will collide more often with the atoms or the molecules here. Mainly atoms, you can use the term atom. So there will be more frequent collision between the electron as we increase the potential. There will be more frequent collision between the charge carrier and the atoms. As a result, what will happen when there are more frequent collision in a semiconductor, such as silicon or germanium, these electrons, if they collide with a molecule or the structure, they can remove the electron out from this bonding. Like if this electron was there from the battery source, this electron knock out the electron from the bonding. As a result, it will produce an electron and the vacancy of the electron, which is called a hole. So when we increase the voltage, there are more frequent collision between the electrons and the atoms. As a result, it produces more electrons or it produces more charge carriers. And you can also say charge carriers and hole pair. When there are more charge carrier and hole pair, so what happened? We have this transport equation I is equals to N A V Q, where V is the drift speed, N is the number of charge carrier. So as there are more charge, like more collisions are there, it will produce heat energy, greater amount of heat energy, more charge carriers. As a greater number of the charge carrier, more current will start to flow, or more charges start to flow. That's why the resistance will decrease. So summarizing this, the first point, the increase in voltage increase the number of the collision between electrons and atoms. And what is the effect of this? Such questions with a static, you should relate the sentences also with each other. You cannot just write one sentence and then second sentence does not have any relation with the first one. So you should use specific terminologies for such static questions as well as relate each sentence with each other. So when in the increase in voltage increase the number of collision between the electrons and atoms. As a result, more collision produce heat energy, which increase the temperature of thermistor. When it increases the temperature of thermistor, the heat energy produce the heat energy will produce more charge carriers or you can also say electron hole pairs. As a result, it increases the conduction or you can say current, which reduce the resistance. So these are the points you should include whenever you're explaining the how the resistance of a thermistor is changes with temperature or increasing in voltage. For a filament, a similar answer is there, but because for a filament bulb, it is inverse. It's when we increase the voltage, there will be more collision, more heat, lattice vibration increase, but the number of the charge carrier does not change, so resistance also increase.